neutron stars, which is even more bizarre. So the first question that we have to address is, what is a neutron? Otherwise, how can we talk about neutron stars? Well, a neutron is an atomic particle that may not tell you very much, but atoms exist of a cloud of electrons, and then there's an extremely small nucleus which contains protons and it contains neutrons. And if you take 10,000 billion neutrons and you line them up, touching each other, it's only 1 inch. So that's how small a neutron is. 10,000 billion, just line them all nicely up, this one. So a neutron is an extremely small particle. Neutrons were discovered in 1932 by someone of the name of Chadwick, for which he got the Nobel Prize. If a star is substantially more massive than our sun, it will not finish its life as a white dwarf, but it actually will become a neutron star. And the way that happens is that this core, this white dwarf, grows and grows in size, grows and grows in mass, and when it reaches a certain limit, it can no longer exist as a white dwarf. Not so easy to appreciate, not even for physicists. In fact, the physics that you need to understand that is quantum mechanics. Why all of a sudden the star can no longer support itself. So this white dwarf like Sirius B, which is perfectly stable, will not survive if I keep adding matter and matter and matter. There comes a limit above which it collapses onto itself. And that limit was actually calculated by a very famous Indian physicist. His name is Chandrasekhar. And for that incredible calculation, which is very simple actually, every graduate student nowadays can make that calculation in 2 minutes. He argued that if the white dwarf becomes more than roughly 1.5 times the mass of the sun, that it can no longer support itself, then it will implode onto itself. And then something else will happen. He didn't know what would happen, but something else will happen. And we now know that what happens is that it forms a neutron star. What actually is happening is that the electrons of the atoms are being squeezed into the protons when the white dwarf collapses onto itself. And when an electron is squeezed into a proton, you get neutrons. So effectively, you have one whole star of neutrons, and that's why we call that a neutron star. And when this change happens, when the white dwarf undergoes this collapse, because there's too much matter on the surface of the white dwarf, there is an enormous fireworks going on in the sky. We call it a supernova explosion. What happens is that the matter falls onto itself, picking up an immense speed, a major fraction of the speed of light. And as we discussed earlier, when you drop something on the floor, you take this, you drop it on the floor, it picks up speed, but then when it hits the floor, it converts that to heat. And so the same thing is happening with the white dwarf. When the white dwarf collapses onto itself, you get an immense speed of this matter, and then it's converted to heat. And this heat then causes an enormous explosion. And a large fraction of that white dwarf matter may be thrown off in space, and there may be some core left over, which then is the neutron star. And it was suggested in 1933 by 2 astronomers, Vicky and Bade, that in the process of such a supernova explosion, you should really call it an implosion, something that falls in, that a neutron star may be formed. They suggested that in 1933, 1 year after neutrons were discovered by Chadwick. An unbelievable prophecy. The whole concept that the white dwarf then would turn into a neutron star. An amazing idea, and to do that 1 year after the discovery of a neutron is quite amazing. So we now understand, at least a little bit, why the white dwarf can, at certain point, gives up, collapses onto itself, and that has to do with quantum mechanics, And that was first calculated by Chandrasekhar, for which he got the Nobel Prize for that calculation. Robert Oppenheimer, you probably know of him because he was the father of the atomic bomb in the United States. And Volkov in the late 30s, 1939, 1930s, they did a lot of work, theoretical work on neutron stars. And they decided that the neutron star would probably end up with a radius of about 6 miles. So this white dwarf then, which is about the size of the Earth, would collapse onto itself, but would become stable again at roughly a radius of 6 miles. And that would then be the neutron star. So now we have a neutron star, which is 1,000 times smaller than a white dwarf. The Earth has a radius of about 6,000 kilometers, and now you make that all the way 6 miles, so you go about 1,000 times smaller. So you can imagine that the density of a neutron star is unimaginable, because if you make the object 1,000 times smaller, then the volume is 1 billion times smaller. And if the same amount of matter is in this small volume, the density goes up. So a neutron star then, therefore, has 1 billion times higher density than a white dwarf. And a white dwarf was already unimaginable. A white dwarf was already 8 million pounds in a gallon. Well, if you have a neutron star, then if you take a teaspoon of matter from a neutron star, you would have something like 500 million tons. All the buildings of Cambridge, Massachusetts, where I live, all that matter could be then in a teaspoon. So it's an unimaginable density. So now comes the question, how do you find a neutron star? We agreed it was already so difficult to find a white dwarf because so small. A neutron star is 1,000 times smaller than a white dwarf. So at first you would think that's pretty hopeless. You wouldn't see any noticeable amount of light from a neutron star. So if you compare, for instance, the sun with a neutron star, and you assume that they both have the same temperature. I do that to make it easy, so that the T to the 4th is the same for both systems. Then the neutron star would be 10 billion times fainter than the sun because of this smaller radius. 10 billion times fainter. So your chances of finding one are not very good. Unless the neutron star is very close, really very close to Earth. So how now were they discovered? They were discovered by a young lady. Her name is Jocelyn Bell. Jocelyn Bell did her graduate student work in Cambridge, England. And she worked, her supervisor was Anthony Hewish. And in 1967, when Anthony Hewish had built a new radio telescope, and Jocelyn was checking every day the results, the measurements with that radio telescope, she noticed one day that a radio signal was received by this radio telescope, which was a signal with pulses. Every 1.3 seconds, there was a little blip in the radios, pulsed in the radio. A weird thing, never been seen before. Radio emission, there are a lot of sources in the sky that emit radio emission, including the sun, but never every 1.3 seconds a little blip. So she discussed it with her supervisor, Anthony, and they said, well, this is, of course, the discovery of the century, because this must be intelligent life. Because who on earth, no pun implied, would send every 1.3 seconds a signal in radio to the Earth, right? So there must be intelligent people. And so they called this object Little Green Man. And they kept it extremely secret. And there's a good reason for that, because now you have the first contact with intelligent life outside the Earth, which is immensely important consequences. So they kept it very secret, and they worked very hard on it, and they tried to do everything possible to convince themselves that it wasn't really something that came from outer space, but that it was produced locally. Maybe an elevator in a building somewhere, maybe in the next town, maybe a motorcycle. And it took them months to convince themselves that it was not made by man, that it was not something that came from the Earth, but it really was something that happened out there in space. And by that time, they found another object. They're called pulsars, by the way. They found another one. It was not exactly 1.3 seconds, but it was also roughly 1.5 seconds. And so they called that LGM number 1, the first one, and the other one, Little Green Man number 2. And then by the time that the third one was found, they gave up on the Little Green Man idea, and they published the stuff in 1968 in Nature, that is a journal, and they didn't call it Little Green Man anymore because they realized that it was unlikely that there would be 3 civilizations doing sort of the same thing to Earth. So they recognized that it was something else. And they suggest in their paper that there could be white dwarfs. They thought of pulsations of white dwarf. And they also mentioned neutron stars as a possibility, pulsations. Now, how the radio emission came out of a pulsating neutron star, that wasn't very clear, but at least they mentioned the word neutron star. And it was that same year that Tommy Gold from Cornell University convincingly demonstrated that what this must be is a neutron star which is actually rotating. And that the 1.3 seconds tells you the time in which the neutron star rotates around. And I will get back to that a little later. If you take the sun and you collapse the sun, all the matter of the sun, into an object which is only 6 miles across, like a neutron star, if you did that, then that core, that neutron star core, will rotate extremely fast, even though the sun doesn't rotate so fast. The sun only goes around in about 25 days. You don't see that because there's nothing on the sun that you can recognize. But if you would look at solar sunspots, if you did that, you could see that the sunspots move from day to day, and they go around in 25 days. If you take that whole sun and you collapsed it to something that is 6 miles across, then it would spin so fast in about 1/1000th of a second. And why it does that, you have to ask your physics teacher. We call that the conservation of angular momentum. Just accept it for now, but you've all seen beautiful women on the ice which are skating, and then they rotate, and then they pull their arms in. And when they pull their arms in, they go faster, and then they pull their arms out, they go slower, and then they pull the arms in and they go faster. That's the same phenomenon. It's exactly the same. It is because of this strange conservation of angular momentum. And for those of you who have had some physics, you will be able to understand that a little better. So from the 25-day rotation of the sun, collapse it all to 6 miles, you end up roughly with a rotational period of about 1/1000th of a second. And so clearly these neutron stars that were discovered by Jocelyn Bell were, in the past, undergoing a collapse and were spun up enormously, in that case, roughly to about a second. Now, why you would see these radio beams going over the Earth is, of course, more difficult. And I will not make a very serious attempt. In fact, it's not even so well understood. Even today, it's now how many years later? It is almost 40 years later, and we still don't understand quite the details of why there are these radio beams coming out. But we do know that neutron stars must have an extremely high magnetic field. In the same idea, when there is a collapse, why it goes spin faster, there are also some basic laws of physics why the magnetic field strengths would go up. And even though some people question whether those laws can still be applied, the conclusion still is that the magnetic field strength must be extremely high on the neutron star. And so now comes the idea that if the star is rotating about this axis, this is the spin axis of the star, but if the magnetic poles are not here and there, but if the magnetic poles, for instance, are here and there, then the poles are moving around, and it is believed that the poles have searchlights of radio beams. And so if you happen to be in a searchlight of this radio beam, so the star goes around like this, remember it rotates about this line, and here are the magnetic poles, then you see a blip, radio blip, you wait a little, there comes another radio blip, there comes another one. And so the idea then is that the magnetic poles should not coincide with the poles of the axis of rotation. So now you will say, well, that's very artificial. I mean, why does it have to be so complicated? That's not artificial at all. You cannot name one planet for which that is not the case. Take the Earth. The geographic North Pole does not coincide with our magnetic pole. Our magnetic pole is somewhere in Canada, and the geographic North Pole is at the North Pole. And they're not the same. There's a substantial difference. And that's the case with almost all planets, with one exception. And I'm not going to mention which one that is. So in all cases, the magnetic poles do not coincide with the axis of rotation. So it's not at all artificial to assume that that also would be the case for neutron stars. So a neutron star is really like a lighthouse. So I want to show you some slides which may make it a little easier to appreciate this formation of a neutron star, which then we believe, at least it was already believed in 1933, is the result of a supernova explosion, which really should be called maybe implosion. So the first slide that I'm going to show you is a supernova. Oh no, the first slide I'm going to show you, no, is Sirius B. Oh, how could I have forgotten that? And how can I turn all these lights off? Oh, yeah, I do this way. Dark enough, yeah. Here you see Sirius B. I forgot to show you that. I don't have to ask you which the faint star is, do I? So this is Sirius A, and this is Sirius B. This is 10,000 times fainter than Sirius A. And you may always have wondered why we call these objects in the sky, why we call them stars. Now you know why. You see? It's a star. Physics is simple. So next slide. Ah yeah, that's what I was aiming for. So here you see a galaxy quite far away, 100 billion stars. You only see the little fuzzy patch, which is the result of all these 100 billion stars together. And in that galaxy here is a supernova explosion. That star belongs to this galaxy. And the light that is emitted in the early part, the first few months, is more than all the stars together in the galaxy. So this one star, which is the supernova explosion, outshines 100 billion stars. There's a tremendous fireworks in the sky. And you see it here a few months later, and again a few months later, and here I think it's about 1 year later. Still visible. So there's a tremendous amount of energy that is released during this implosion. In fact, the amount of light, the amount of energy that is produced as a result of this collapse is more than the star has produced in its entire lifetime. So if, for instance, our sun lives 10 billion years, it's 5 billion years old, has another 5 billion years to go, so 10 billion years, it would have emitted less energy in that 10 billion years than it would emit in a matter of a few weeks to a few months if it undergoes a supernova explosion, which our sun will not, because it's just not massive enough. But it gives you an idea of how much energy is released in that collapse. And now we're going to see Jocelyn. Next slide, please. This is Jocelyn Bell in her good days when she discovered it. If you focus a little better, you can see here this radio signal. Yeah, that's nice. So from here to here is 1.3 seconds. This is a time scale. And you see clearly this radio signal is very periodic. She became very famous, but not famous enough in my book, because Anthony Hewish received the Nobel Prize for this in 1974, and she did not share it. And that, I think it's fair to say, is an incredible injustice. She was the one who discovered it. She was the one who pursued it. She was the one who convinced Anthony that indeed it was something in the sky and not something on Earth. And yet she did not share in the Nobel Prize. And this will always remain a puzzle to all of us, and we will never know why. Maybe it was because she was a woman. That would be a terrible thing, but it's possible. This is a male chauvinistic society. At least it was even worse then than it is now, but it is still pretty bad. Or maybe it is because she was a graduate student. Or maybe even worse, she was a graduate student and a woman. In any case, she did not share in the Nobel Prize. And I've discussed this with her more than once, got to know her quite well, and she is quite modest about the whole thing. She says, well, Anthony was the one who invented this new telescope, and I was just doing my job. Well, yeah, doing your job, and then in the process discovering neutron stars. She's too modest about it, and there's no question that Jocelyn should have shared the Nobel Prize. Next slide shows you then a sketch of an idea of a rotating neutron star. So this is the axis of rotation, rotates around, and these are the magnetic poles. Notice they do not coincide with the axis of rotation, and it is believed then that there is a very narrow searchlight, but not in light, but in radio. And so that rotates around, and if you are on Earth and the beam hits you, then you see this blip in radio. This doesn't tell you much, but it gives you a rough idea. The next slide shows you a supernova explosion, which happened actually quite nearby. Now, when you think of nearby, you may think somewhere around the corner, but for astronomer, 150,000 light years is nearby. And this object is about 150,000 light years away from us. So it takes the light 150,000 years to reach us. So the explosion actually did not happen on February 23, 1987. That's when we noticed it. On February 23, 1987, it was discovered, it was seen, but it happened, of course, 150,000 years earlier. And it's been given a name, it's called 1987A. 1987 refers to the year, and A refers to it that it was the first supernova that was discovered that year. And believe me, the number of papers that have been written on 1987A is probably more than 2,000 or 3,000 ever since then. It was observed in every conceivable wavelength, in every conceivable telescope that you can imagine, in the radio, in the optical, in the infrared, in the UV, in the X-rays, in the gamma rays. It's one of the most famous objects in the sky, and it was, of course, a prime target for the Hubble Space Telescope, which was launched substantially later. And so here you